Right. Okay, so we start our second lecture in this course of Physics Beyond the Standard Model. And as we discussed yesterday, that we will have 5 lectures. The first one we did, it was overview of a standard model. Today we will consider 2 simple examples of possible extension to the standard model, one based on U1 prime or U1 B minus L. Try to convince you that B minus L is much natural, is very natural U1 extension. But of course, there is several general U1 prime extension. We will mention to this as well. And hopefully we will have time to also discuss 2 Higgs doublets today. Otherwise, we will have a separate lecture for 2 Higgs doublets. But I hope we can have these 2 examples in one lecture so we can have more time for more detailed model in the next lectures. So today I will start with what's called the TV scale B minus L extension to standard model. And as I mentioned, also we may discuss 2 Higgs doublets. Yesterday we said the standard model is based on the gauge group SU3 cross SU2 cross U1 hypercharge. And in fact, we also mentioned that neutrino is massless, or neutrinos are massless. And in fact, there is no right-handed neutrino. And the whole point is now to extend standard model and to find a way to generate the neutrino masses. Of course, one can say, okay, I will just add right-handed neutrino to the spectrum of the standard model. I tried to argue yesterday that gauge symmetry is really very successful mechanism for deriving a force of constructing the standard model, taking U from the electrodynamics to the weak interaction, to strong interaction, to the whole picture of the quantum standard model. This mainly was based on the gauge group. So if we wanted to go beyond the standard model and to find solution and the mechanism for neutrino masses, maybe is preferable to go do it via some extension of the gauge group as well, which guarantee for you to include some type of singlets fermion under standard model, which we will call it right-handed neutrino. So it comes naturally in this case. This is exactly what we will do here. And why B minus L? For several reasons. First of all, standard model itself has a global symmetry, B minus L global symmetry. So the baryon number is known, which is quark is 1/3, and lepton number is known, where leptons has a charge 1 for lepton. So B minus L is known for all the spectrum of the standard model. Fermions, of course, is a Higgs is 0 B 0 L, so B 0 B minus L. However, this symmetry was there in the standard model as a global symmetry. So naturally, to think about make it global as a local as other symmetries. So this was already exist in the standard model, but as a global symmetry. So the idea, maybe it was a local symmetry at some high scale, and then when you break it, you will have a remnant global symmetry, the B minus L, which we already have it in the standard. In fact, why not B it's by itself or lepton by itself? Well, because the anomaly cancellation and anomaly free, B minus L is doing better. So in fact, the combination of B minus L is one of the interesting examples. We have it as a global symmetry. We have it as a natural quantum numbers in the theory. Moreover, any theory at Got scales, usually you have B minus L. In fact, you have B minus L and the B plus L. and the B plus L is broken in directly, and it remains with B minus L as exact local symmetry. And as I said, it can be broken at some lower scale and then remaining just a global symmetry at standard model scale. So this is would be nice formalism or structure or framework for this. But anyway, today we will do a bottom-up approach. We will just have the standard model that we discussed and extended by extra U1, okay? And then I will try to show you how things is changed. Very simple extension, just add extra U1. And the U1 we know, we will not invent. In fact, if we consider this is not U1 prime, you will have to ask what is the charge of the quark, lepton, Higgs under this U1 prime. And the charge is not completely arbitrary. It's not completely arbitrary. You have to admit what we call now, if you know the quantum field, what's called anomaly cancellation. The theory should be anomaly free, so the charges is not ad hoc. Having B minus L guarantee this. Charges is well defined. Anomaly cancellation, you will see, very simple to prove it. So things is, and very natural because it gives you right-handed neutrino. It doesn't give you something extra matters, but the matter that you needed for the neutrino sector. For that reason, I was interested in this. It was master exercise for one of my master students. He's now associate professor or so, but he did this exercise because everybody was considering B minus L in GAC models and at very high energy scale. So I think in 2008, with him, we decided to check this scenario at TV scale, and then we implemented in even supersymmetric version and proved that yes, it can be at TV scales, and then the model becomes B minus L is known, and the supersymmetric B minus L is in the high energy physics tools, and a lot of work done after that with my colleagues in UK and so on. Okay, so this is now the gauge group. You know, each model we have to know the gauge group because this is where we define the interactions and the spectrum and then the Lagrangian, of course. So now the spectrum, as I told you, the standard model, all standard model spectrum will remain intact, the same. We have extra U1, the charges, as I told you, is fine. But remember, the standard model was anomaly free. All the triangle diagrams that you have it from the gauge boson, mu, mu, for the weak or strong or the electromagnetic was cancelled identically in the standard model by itself. Now we add something else. Can we make it also free of anomaly or anomaly free? Yes, but you need another 3 fermions. Singlet under the standard model and has a charge B minus L as a lepton, so it has -1, charge -1. So it's not baryons, but has -1. This is the only, first of all, you need this 3 fermions, and it should be 3. You know, also because in the neutrino, you need right-handed neutrino, but how many? 1? You cannot make it with 1. 2, yes. 4, 5, 6, any number, yes. But here the number, people usually use 3 because we have 3 families of fermions. So the right-handed neutrino comes in 3, but it is a singlet. It is different from the 3 families of. So in principle, it can be any number. However, here, due to the anomaly cancellation and the anomaly-free conditions, you have to have 3 singlet fermions. First, we call it 3 singlet fermions. We find that it has a charge -1, so it is leptons. And we find that it couples with left-handed neutrino, left-handed leptons, and they work as right-handed neutrino. And then we said, yes, this will work as our right-handed neutrino. And in fact, here we give the annotations that you write on. As any gauge symmetry, this is local gauge symmetry, so it will have mediate gauge bosons. associated with gauge boson. The U1 hypercharge, the U1 electromagnetic, the photon, the A mu, W plus W minus for SU2, and this is will have another gauge boson. We call it ZP minus L or Z prime. So this is another extra neutral gauge boson. Neutral in the sense has no electric charge, but it has a charge, of course, or it is a generator, or it is a gauge boson associated with the U1 B minus L. So this is a second addition. You see, you just wanted to solve the neutrino masses. You decided to extend the gauge group with extra U1, the simplest extension possible. And the best and the most simple U1 is a B minus L. You find that you need 3 right-handed neutrinos to make the theory consistent, quantum mechanical or quantum field theory, and to make the U1 B minus L is anomaly free as well. Good, and then you need some Z prime to be associated as a gauge boson of this one. And last and not least, you break this U1 because it is not low energy. So you need some, of course, the Higgs, our Higgs is a B minus L singlets under B minus L singlets. You know, sometimes we call singlets means the standard model. But B minus L, the Higgs, has a 0 charge, B minus L. So it's not charged under B minus L, and therefore the vacuum expectation value of the Higgs cannot break B minus L. It breaks the U1 hypercharge because it has a hypercharge, and it can break the SU2, as we said yesterday, because it is doublets under SU2. But is it chargeless under B minus L? So it cannot break the B minus L. So who will break the U1? We have to add extra singlets, and the extra singlet scalar, chi, this is chi, and this chi will be charged under the B minus L. See that it may have +2 other charge to be able to build a term in the Lagrange. So this is the new particle, or this is a particle. Forget about the quark sector. So you have the lepton with B minus L minus 1 because it has B equals 0, L equal 1. E right is -1. Mu right, similar to E right, will be -1. Phi, the scalar Higgs, standard model Higgs, is 0 under B minus L, and this extra scalar is chi, it has a charge +2. So this is new particles, have a significant impact on the standard model phenomenology, and also interesting LHC results signatures, as we will see. Okay, so now do the same exercise of the U1 electromagnetism that we started with. It is a U1. So again, we will say, yes, we have phase shift where all fields is invariant under this phase shift, but now we wanted to make it local. So we take the parameter theta to be theta of x. And the quantum number is y b minus L, as exactly we did in the electromagnetism or the hypercharge. Now we have left-handed and right-handed. In fact, both left-handed and right-handed are transformed under the B minus L because both are charged. It doesn't matter really left or right. It matters only if it is lepton, it has -1. It is baryon, it is B 1/3. If it is Higgs, it's 0. So in principle, the left and right, psi left and psi right, will have the same transformation, the phase shift transformation. Here is local because theta, the parameter of the transformation, is function of x. Then we absorb this, you remember partial mu psi will produce partial mu theta, and to absorb it, you need to add some extra field, the gauge boson. This is what we call it now Z prime, or Z B minus L, or whatever. I call it here C, and later I will call it. So you absorb this with the same mechanism of the gauge transformation, and you construct now another term for the B minus L, which is essentially 1/4 C mu nu, C mu nu, like F mu nu, F mu nu. We have B mu nu for the U1 hypercharge. And this is a weak interaction, which is SU2. It's non-abelian, so it is W mu has an index A1, 2, 3. If you remember the story of yesterday. So this is a kinetic. This is a gauge part of the language. Now we come to the fermion part, which contains covariant derivative d mu. And the d mu now, it contains, as usual, the normal derivative plus the shift or the addition of the gauge boson. So now, for left-handed, d mu partial d mu psi L will be partial mu plus IGW for the SU2. This is cycles. And G prime B mu. This is a hypercharged Y. The left hand is charged under SU2. So we have this gauge boson here. Is it charged under the U1 hypercharger? So we have this term here. Is it charged under B minus L? Therefore, we will have IG double prime, or we call it GBL, GB minus L, and times YB minus L, and the gauge boson of the B minus L. So normal structure, normal procedure. For psi L, for psi right, you can imagine it will be charged under B minus L, so it has the same term. Hypercharged will give the same term, but not SU2, because this is right, and this will be d mu psi right. Okay, so nothing really new. Please.
So now that the right neutrinos still can't interact through weak interaction, right?
Weak interaction, no.
Yes,
but it will have new type of interaction.
Yes, this new type of interaction, its carrier is Z prime.
You will see it will have two type of interaction: Z prime, the B minus L interaction, and the Yukawa interaction. Because now you can build. Just in the next slide, you will build Yukawa term for right-handed neutrino with left-handed lepton. This was missing in the standard model. So this will be the Yukawa interaction, which part of it will be the mass when it takes a vacuum exclusion value, and also some kind of interactions that we will see.
So Z prime represents like a new interaction.
Yes, like Z boson.
Yes, but like the boson, but not responsible for mediating any fundamental interaction.
No, it is by itself fundamental. It is by itself. This is, we call it even fifth force. Yeah. If it is happened and we discovered Z prime, this type of Z prime typically is heavy. You will see above TV scale. So it is rather heavy, and the LHC is making a lot of effort to observe it. But in principle, some scenarios, maybe not B minus L, but some other U1 prime, you could have Z prime to be quite light. And this is in general, the people talking about, because it looks like the photon, it's just a U1 abelian, so they call it dark photon sometimes. They call it fifth force sometimes. All this is just simple U1 prime. Okay, but it is, the word fundamental interaction is not limited to our standard model interaction. Any new interaction you will add, it will be fundamental. Fundamental means it is not coming from any other origin or other source. It's fundamental by itself. Okay, so this is in this sense. This is the anomaly free, that anomaly conditions that I was talking, the triangle diagrams. I don't know if you have seen this before in quantum field or not, but any theory, you have to check that there is no anomaly in this theory. So this is example of the anomaly cancellation of the model B minus L, and without right-handed neutrino, or without what we call it singlet fermion, this will not give free cancellation, because you will see it now. To cancel this, you have to satisfy all this equation. So for example, if you take the hypercharge, what we call it B mu, for example, the gauge boson B mu, you need B mu, B mu, B mu. this is a standard model. And the three level, the singlet fermions, the right-handed neutrino is not coupled with them. So this remains as a standard model. So it cancels. W, it cancels as normal. Now, once you have C mu for the B minus L with B, this is now will give you something. In fact, this is, we said B, C, yeah, anyway, now if we have W from the SU2 and the hypercharge, this is like standard model. Again, this diagrams will give you the trace of the generator, tau I, hypercharge. Hypercharge is a constant, it goes outside the trace. It will be trace of Pauli matrices. Trace of Pauli matrices is zero. This is identically zero. But this is a standard model because this is WSU2, U1 hypercharge, U1 hypercharge. So this is a triangle of this three interaction. Now, SU2, B minus L, B minus L. Okay, in the same way, it will be proportional to the trace of the Pauli matrices will be zero. So it is fortunate. Doesn't really depend now about the right-handed neutrino, because right-handed neutrino, in fact, it doesn't really run in this loop because there is a W in one vertex, there is a W, and the W cannot couple with right-handed neutrino. Now, this is again W B minus L. It will be proportional to trace B minus L, and this should be zero. But without singlet fermion with a B minus L equal -1, standard model by itself, if you count standard model, you have how many quark? I'm running here. So the trace of B minus L will be sum over all the charges of B minus L. Imagine that you don't have singlet fermion, okay? You want this to be zero. You sum, you make the sum. I did the sum. You take all your quark. I don't know how many quark we have. We have 6 times 1/3. For each is B minus L 1/3. And then you go to for leptons. How many leptons you have? You have left-handed leptons, and okay, you count, and then you will see that it cannot give you 0 unless you include right-handed neutrino 3 with minus sign -1. The sum of all the charges with existing right-handed neutrino will give you 0, 0, and will make this equal 0. Same story for this one, trace 3, B minus L, B minus L, B minus L, depends on the sum. Also the trace of 2 B minus L with hypercharge, all the combination. You will find all combination will vanish under 2 conditions. First of all, the trace of the Pauli matrices, in case of you having gauge boson of SU2 will vanish, and the trace of or the sum of the hypercharge, the sum of the B minus L charge should really, the sum should be 0. Sum of all charges. Exactly like in the standard model. Why it is anomaly free? Because the hypercharge of all particles, when you sum it, you get 0. Okay, so all charges, for example, the doublet, the quark doublet, Q, which has a UD, it has a hypercharge. It depends on the convention 1/6 or 1/3. I think 1/6. And then the U right, and then D right, and then leptons, and so on. You do this exercise and make the sum for hypercharge. You will find that the sum of the hypercharges is 0, and therefore hypercharge in the standard model was anomaly free. But if you sum B minus L for only standard model particle, will not vanish. When you add singlet fermion with a charge -1, will vanish, and it will be anomaly free. And this is the reason why we need to include right-handed neutrino.
So
you got it?
So normally in standard model we should have the sum of the hypercharge, for example, from a particle like proton. If we sum the hypercharge.
No, I'm not talking about proton. I'm talking about the whole particles play role in the standard model. You see these diagrams for the fundamental interactions. So we have a SU2, SU2, SU2. So you have to run all particles with the SU2 interaction in this quarks, leptons. Right? You include, you run, of course, SU2, 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 you will not add U right or D right. You will add just the Q left and the lepton left, and that's it. You run and you see that this is vanished. But it's vanished not by the sum of the charges. Vanished because this is SU2 by the generator of SU2. When you have hypercharge, everybody in the standard model is charged under U1 hypercharge. E right, D right, U right, lepton left, Q left, everything. You sum over all these charges because all of them are running in the loop. So you need to guarantee that the result of this loop, which depends on the trace of the generator. And this is U1. So the generator is just the charge times the identity, and you sum all of them together. So this will be identically zero naturally from the definition of the hypercharge we proposed for the standard model. Now, B minus L, for only standard model particle, it will not work. You need singlet Fermi with definite P minus L to P minus 1 to give you this result. Okay?
I mean, we have to get this, the sum of hypercharge equals zero in a specific interaction, or in general, I just get
not general, not specific. It depends on each diagram. How many gauge bosons you have, how many interaction you have. In standard model, you have 3, right? So in the standard model, if you start with SU3, SU2, then you will have here the gauge boson of SU2. You could have here gauge boson of SU2 and the gauge boson of SU2. So these 3 gauge bosons in this diagrams will be SU2. For that reason, we call it SU2, SU2, SU2. This is 1. You check 3, cancel, okay. Then you go SU2, U1, U1, U1 hypercharge. You check SU2, SU2, U1, 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 U1. You have to go for all. This is external photon. This is external gauge boson. So external, there is no sum over external. External, you have to replace each time with one of your gauge boson that you have. So you run it for SU2, and you check, you run it for U1, and you check. Now you run it for U1, P minus L, and you check. In the loop, you run over all allowed particles to be in the loop. Okay? Because the loop has a sum over all particles. But external, it is fixed, and you check it one by one.
So it's a generalization of Curie theorem, where
which theorem?
Curie theorem, where you have a number of external photons, for example, and you have a loop, and they cancel, or it's different.
No, this is not necessary to cancel automatically. This is, as we said now, B minus L. It can be non-zero if you do not add extra singlets, the right-handed neutrino. So yeah, this is really one of the criteria when you are building. Hopefully in the future you will build. In fact, one of the exercise, I am happy that we discussed this, because one of the exercise assignment, I will leave it to you, when we change B minus L and we have just U1 prime and we don't know the charge, how we will determine the charge? From this, because you will have now U1 prime, U1 prime, U1 prime, and U1 prime, U hypercharge, U hypercharge. You have to check all these equations and to satisfy. And when you have set of equations and you have freedom in choosing the charges, you started to solve the set of equations for set of number of charges you determined. No, I wanted this exercise to be clear in your mind to do it. So I will ask you to consider U1 prime, okay? And assign Q1 or P, call the charge whatever. Q1 for quark, Q2 for lepton, Q3 for, I don't know, right-handed quark, and so on. Even Higgs, give it charge. And then I will ask you to determine the charge from anomaly cancellation. You need to guarantee that the anomaly is cancelled. So when you have the sum, you will have equation, linear equation between the charges. because, for example, the trace B minus L will be the charge of the quark plus the charge of leptons plus the charge of this and this. You have several equations, give you several constraints on the charges. You solve it together, and then you come with possible charges in this case. You will find that in case of you take the charge 1/3 for quarks and the -1 for leptons, you will get B minus L automatically, and the right-handed neutrino as well. Okay, so this is the condition for consistency condition for the B minus L to be anomaly free. Okay, online colleagues. Okay, now we are satisfied. We agreed that somebody wrote something. Muradi said yes. Okay. We agreed that U1 is anomaly free, is nice, we can use it. But you didn't ask. In this diagram, you see the solid line means the fermions running in the loop. Okay, this triangle does not include any scalars. So the Higgs phi or the Higgs chi cannot contribute in this diagram. I told you, you have to include all particles allowed for this type of interaction. So my questions to you, why the scalars cannot contribute in this triangle diagrams, in this anomaly cancellation? Okay, we run only for the fermions. We run for quarks, leptons, and we found it's not enough, so we include right-handed neutrino. What about the Higgs phi and the chi? Is it possible to include it here or not? I keep it to think about it. It's very simple, by the way. And based on the information you know from the quantum field in general.
In the final rules?
Yes.
So it's not included because
scalars?
Yes, scalars are not included.
Yeah, because the scalar has an interaction or has a vertex with a gauge boson as a two gauge bosons and two scalars. You know, when you have d mu phi, d mu phi, d mu will give you. So you could have always two scalar, one gauge boson with partial derivative, or two gauge bosons and two scalars. The fermions, because it is a psi bar d mu psi, you will have a two fermions and one gauge boson. So you could have a vertex, three particle gauge boson, two fermions like this from the Lagrangian, from QED, from the standard model, from all the quantum field essentially. So for that reason, the anomaly cancellation rely only on the charge of the fermions. Okay, now we as usual, we invent a symmetry and then we break the symmetry. People are sometimes saying you are joking, why you invent it if you wanted to break it. But we discussed this before, that it is very important to have a symmetry to guide you, and then when you break it approximately or spontaneously, so still your Lagrangian feel the symmetry, and your theory is controlled by symmetry, but only the vacuum is breaking the symmetry and generate mass for the gauge boson. Because without breaking the symmetry, Z prime will be like the photon, will be massless. And of course, we cannot accept this. So how to break it? This is the chi field, the scalar field that we included exactly for this purpose, to break the symmetry. So we will have a potential for the scalar for the scalar chi. This is a potential now in this model. So you see the first part, m1 phi square lambda phi to power 4. This is the standard model potential Lagrangian for the scalar in the standard model that we discussed last time. Now we do similar potential, similar interaction, similar potential m2 chi square, m2 square chi square, and lambda 2 chi to power 4, very similar. But now we could also have a cross term because the symmetry B minus L and hypercharge and SU2, everything allows for phi dagger phi is invariant by itself, chi dagger chi is invariant, so the combination will be also invariant with coupling lambda 3. So as I told you, usually you want to add something, you will find that it is growing from you. Sometimes growing too much that you cannot control it, but here it's, for this is simple, and for that reason I'm saying that still it's the simplest extension. So we add 3 types of particles, right-handed neutrinos, scalars, and gauge boson. And now we have the potential with even extra term. They are not just 2 separate, they are talking to each other via lambda 3. And now we will have some conditions. You remember when we started the potential of the standard model, we said lambda 1 phi 4, lambda 1 phi 4, lambda 1 should be positive to avoid or to guarantee the potential will be unbounded from below, doesn't go to infinity. And now also lambda 2 should be positive for the same reason. But now we have lambda 3, so in fact some condition on lambda 3 to satisfy these values. You need to check because when we have 2 fields, now you need, how we get lambda 2 positive and lambda, you need to make this minimization, and there is some matrix, it's called Hessian. It should be rather positive, and you know this is will give you condition, because when you diagonalize, when you make the minimization, you will have lambda 3 in the off diagonal and lambda 1, lambda 2 on the diagonal. So the issue is not lambda 1, lambda 2 to be larger than 0. The whole Hessian should be positive definite, so lambda 3 should also be larger than these values. Okay, and this is a condition known when we have 2 scalar fields in one potential. We do this and we minimize.
Potential we have to assume M1 squared.
No, we will. Otherwise you will not get a vacuum non-zero. Still you need M1 square and M2 square should be negative. Okay, still the same problem of minus mass square that we want. However, the most urgent first is M2, because you wanted to break B minus L first. So M2 will be negative, okay? And you break the symmetry and you generate the vacuum for chi with a new verb, we call it V prime. As normal. Imagine that we do the breaking at 2 different scales. One at high scale, 1 TV, 10 TV, 5 TV, whatever scale of the Z prime and the B minus L symmetry break. At this scale, you can imagine that phi is still at the 0. So you don't need urgently at this scale M1 squared to be negative. Okay, keep it positive. And when M2 is negative, you break and you get V prime. Okay, is it V prime is broken? So now chi will be shifted. In this term, we will have lambda 3 V prime square from here, phi squared. This will be summed with M1 squared, right? Again, we need urgently to break B minus L first. So we need to assume M2 squared to be negative. And then we generate the vacuum V prime. Then we do shift of the chi field with a vacuum V prime plus chi prime, the new field, as we did in the Higgs. Now this term, which has a cross term, will get chi prime, phi dagger phi. This is the interaction with the chi prime, that's fine, keep it. But also the V prime will give you V square times lambda 3 times the phi dagger phi. This is exactly like this one. So the mass term of phi dagger phi will not be only m1 square, but m1 square plus lambda 3 times v prime square. V prime is large, okay? Lambda 3 could be negative, okay? Then this combination could be negative even if you start with m1 square positive. And then you break at this scale B minus electro weak once after breaking the minus. So you don't need, but this is still required, this is to be negative. We can assume to be in the safe side m1 square negative, but I prefer to look at the following way that I mentioned, that you have m2, which at high scale, and the bare mass of the chi to be negative. It's enough to start with. You generate lambda 3 has to be negative with a v prime. You combine it with m1 square, you get negative mass, and then you break this. This is, in fact, done in this kind of minimization of the plot in mathematics. I take v of phi and the chi, and you will see that the vacuum excitation value and the v prime are quite related. Here is v prime in terms of v, but you could also write v in terms of v prime. But the idea that you can work out to make v prime TV scale and the v 100 GV. Okay, again, lambda 3, positive, negative, depends on the details. So even if you take it with negative minus sign, but larger than minus sign, 2 square root lambda 1, you get v prime much larger than v, and this is low scale v prime of order the electron weak 1 TeV or so. But the second option is when you take lambda 3 positive, the v prime will be quite high scale. Okay, after breaking B minus L, as usual in any U1, you get the vacuum expectation value. The first particle will fill the vacuum and they get mass is a gauge boson of this interaction. So Z prime is a gauge boson of the B minus L, which coupled strongly or gauge coupling, has a gauge coupling with the chi field, which you get a V prime will generate the mass like MZ or MW or whatever, and this mass will be a gauge coupling of the B minus L times the vacuum expectation value of B minus L. So you generate mass of Z prime for G double prime V prime square. And the constraints from the search on the Z prime, especially from Lab2 and the LHC right now, is giving some condition on the ratio of the Z prime over the gauge double prime or the gauge boson. And this should be of order few TeV. So still, if you take gauge coupling of order 1, bracket, order 1, then V prime of order TeV. V prime of order TeV or Z prime of order TeV. But if you take G double prime 0.5, for example, half, MZ prime will be of order few hundred GV. So it's not necessarily that MZ prime to be TeV. The constraints nowadays mainly assume that Z prime is quite heavy and of order TeV, but this relation is always giving the ratio between the mass over the gauge coupling. And the mass over the gauge coupling should be of order TeV. Okay, we are doing the whole extension to generate neutrino masses. Now, can we generate neutrino masses? Yes. Why? Because right-handed neutrino has a B minus L charge minus 1. And neutrino right will give charge minus 2. Chi, for that reason, we choose chi to be plus 2, since it is not entering in the anomaly cancellation, so the charge of chi is free, essentially. We choose it to allow for this interaction. Then you have chi equal to new right minus 2, the sum is 0, so this term is infinite. And why we are interested in this term? Because when chi got a vacuum expectation value, the right-handed neutrino will acquire mass. And you see now, the right-handed neutrino itself will get a mass with Higgs mechanism, with a B minus L symmetry breaking. Chi will get a VEF, then the mass of the right-handed neutrino will be lambda nu right times a V prime. And this will be the mass of the right-handed neutrino. And then now the mass of the right-handed neutrino will be fixed by the scale of the breaking of B minus L. It's not any mass, not 10 to minus 10 to 13, to 10 to 11, 10 to 3, 10 to 4. It's not an arbitrary number. It is related to the vacuum expectation value of breaking the symmetry times lambda mu. And the vacuum expectation value is related to mz prime, and this is a search at LHC running. And also V prime is related to the minimization conditions and so on. So somehow everything can be really controlled. Okay, I got the mass of the right-handed neutrino, not the left-handed neutrino or the light neutrino. Okay, just to previous this. Now also from the Lagrangian, seems I did mention here. Yes, in the Lagrangian where we have Yukawa coupling. So in this Lagrangian, I wrote L Higgs plus Yukawa. L Higgs we discussed it. And now the Yukawa. This is our usual Yukawa. Remember, electrons with E right with phi, and we said doublets, and singlets. So this is, and the phi get vacuum expectation value gives the electron and electron masses. Now we will have something similar. Lepton part, neutrino right, non-neutrino right exist. And now we could have phi, not chi. Why not chi? Chi singlets. Lepton is doublets. So we need doublets, similar to this one. And similar to the quark, when we have up sector, we use phi tilde to have the vacuum up, not down, because down would give mass to the electron. I now wanted to give mass to the neutrino left, neutrino right. So this will be via phi tilde. And phi tilde will link neutrino left from L bar, neutrino right from this singlet, with a vacuum V, not V prime, because this is phi lambda nu. So this is what we call Dirac neutrino mass. So we have right-handed neutrino mass, Majorana neutrino mass, and we have now Dirac, which comes from left and right mixing. So this is, we said, after electroweak symmetry breaking, phi got a VEF, we got the mass, as I told you, lambda nu, which comes from this part of the Lagrangian, lambda nu times a VEF. And this is give you what we call the MD. This is not the physical neutrino mass. Why it is not physical neutrino mass? Because the mass matrix is not diagonal yet. The Dirac neutrino mass, it goes in the off diagonal, MD here, because it is neutrino left, neutrino right. Neutrino left, zero. There is no term contribute to neutrino left, or LL, because. And the MR, we got it from nu right, nu right. So this is will be like 2 by 2 matrix, but each one of those is 3 by 3, in fact, because we have 3 families. So MR is lambda R, lambda nu R chi. Chi is a V prime, and the lambda, this is 3 by 3 Yukawa coupling. We could have here nu R I, nu R J, because this is 3 right-handed neutrino. So there is index I and J. So you add nu R I, nu R J, this is lambda and J. So this is matrix 3 by 3. So MR, I wrote it as a just single, with just simple MR, but it is matrix 3 by 3. MD is the same story, 3 by 3. So this matrix really is 6 by 6. Okay, but usually it is much simpler to write it in 2 by 2 to 3. Okay, now what we will do with this matrix, we need to diagonalize it, because this is in the gauge eigenstates. We need to go to physical and mass eigenstates, so you need to diagonalize it, and you get mass of the diagonal entries, the 4 physical states. So the diagonalization done easily, especially we assume MD much less than MR. So you can cancel higher order of MD over MR. You get very light eigenvalue. One eigenvalue is light, one eigenvalue is heavy. We call it neutrino left now, neutrino L. L now stands for light, and the neutrino H, which stands for heavy. So the neutrino heavy is essentially MR plus some correction of order MD over MR you can see. Okay, so it's essentially MR. This is neutrino heavy. So the neutrino heavy is essentially the right-handed neutrino. Now the neutrino light will be is given by the MD square over MR. MD square over MR. And this will be the mass of the light neutrino of order electron volt, order 1 electron volt or less. So in fact, people was usually consider MR not in B minus L, but in general ad hoc addition of right-handed neutrino is of order 10 to 13. To say that MD, if it is of order electroweak 100, then 100 times 100 10 to power 4, you need to divide it over 10 to 13 to get 10 to minus 9, and this will be 1 electron volt in GV notation. Okay, but now MR, I cannot push it to 10 to 13. I have it from B minus L, TV scale only. So TV scale, this will require to get electron volt MD to be 10 to minus 4. 10 to minus 4? Yes, 10 to minus 4. MD is coming from the electroweak. Remember, the electron is coming from the vacuum expectation value V times the Yukawa, and is of order 10 to minus 4, in fact, because it is lambda times a vacuum, which is 100 GV, you multiply by small Yukawa, and you want the electron, how many? Half MeV. So almost 5 times 10 to minus 4. So we are not far. We are saying the MD of order the electron mass. Why we should really worry about 10 to minus 4 for the neutrino and the MD rack, not M itself, in the mass itself, and we accept 10 to minus 4 for the electron. So if you take it 10 to minus 4 and you divide it over TV scale, you get M neutrino of order electron, M neutrino light of order electron volt. So this was quite acceptable by us and by the community, because it's not, as I told you last time, not very comfortable to say I have right-handed neutrino at 10 to 13 GV, just came to make this CISO, this diagonalization, and this is called the CISO mechanism, to make this CISO and do nothing else. Here we have really physics. We have Z prime, we have chi will play a role, have neutrino right will play a role, and generate mass and really have some other impacts. Okay, so
we can consider that since the order of the using the left and neutrino.
What is the mass of left-handed? There is no mass of the right-handed, because this is my Urana, and new right has a mass by itself. Neutrino left has no mass. So there is a mixing new left, new right. New left, new right. This will give the mass, what we call it MD, and this is go to the off diagonal, not the diagonal.
I mean the measure of the mass, which is not exactly here.
Oh yes, yeah. You can now you need to check that this is the eigenvalues. You need to check the eigenstates. You know, when we diagonalize matrix, you get 2 eigenvalues. You need to get 2 eigenstates, and then you see the heavy neutrino, the eigenstates. Imagine psi 2, for example, the second eigenstate, or psi nu h. You will find that it is the coefficient times psi neutrino left times the coefficient C2 psi neutrino right. I agree with you that mainly C2 will be much larger than C1 in this case. And when you go for the eigenstates of the neutrino left, you will find that it is C1 is larger than C2, so it's mainly coming from the left-handed knot. But of course, there is some contribution. C2 is not 0, and the C1 in the other case is not 0. Linear combination, but usually in the linear combination, if C1 or C2 larger than, I don't know, 0.5, 0.6, 0.7, we are saying that mainly comes from this part. Okay, so in this sense, yes, the light mainly left, the heavy mainly right, because it is not possible to have two eigenstates, two eigenvalues coming from the same state. You cannot have nu H mainly from the right and also the left mainly from the right. Have small contribution from the right. By the way, the small contribution from left and right mix here and there, C1 and C2. This is the one will combine or make the interaction of right-handed neutrino with other standard model Fermi. We will come to this point. When you diagonalize and you get eigenstates, imagine epsilon neutrino right originally doesn't interact with electrons at all, with W boson, but W boson is better because right-handed. But neutrino left coupled with W boson. Now neutrino left mix with neutrino right, and we have neutrino light and neutrino heavy. Okay, so now neutrino heavy in principle via this small mixing will be able to interact with W with very small mixing. You understand what? Okay.
Excuse me.
Yes, please.
The mass basis, why is it fixed component?
Because you don't have in the Lagrangian any term give neutrino left mass. Neutrino left set in the doublet L, and the neutrino left set in the doublet L. So you need in the Lagrangian something LL times some. You know, if you want to use LL, you need to have another triplet to allow this doublet triplet as a singlet. But we don't have. You cannot have LL by itself. Okay. Otherwise, we will not go to any right-handed neutrino and you generate the mass just from left-handed leptons. But apart from, there is a model with a triplet. You could have left and the triplet, but we don't have this. And in this case, you cannot really have any term to contribute to neutrino left. Okay, because doublet is not, even if you make L bar L as a singlet, is not invariant under hypercharge, it's not invariant under many things, okay? Okay, so we consider now, I think we consider one of the spectrum, okay, minimization and Z prime, and then the neutrino. Let us consider the Higgs. I told you the Higgs is playing good role. I hope I will finish how I do have sometimes for two Higgs doublet. Okay, but this is also Higgs boson in BLSSM. In Higgs, in BLSSM, the Higgs sector now, in fact, is not two Higgs doublet, is not one Higgs doublet in like a standard model, but it is one Higgs doublet and one Higgs singlet, chi. So it is mixed between singlets and doublets. So, okay, we have one complex SU2 doublet, the standard model, and one complex scalar singlet chi. Complex. So you know the complex in the standard model, we have the doublet phi, which is complex, and in fact, it has how many 4 degrees of freedom as a complex doublet? 4. 2 in the first component, second 2. And then we combine the 4 to charge it, one singlet, one pseudoscalar, scalar and pseudoscalar. And we told you that 3 of them were eaten by Z. Pseudoscalar component is eaten by Z because Z is CB odd, and W plus W minus have eaten H plus H minus, the components Goldstone boson, charged Goldstone boson. So we end from the 4 to only 1, okay, which is a physical Higgs. Now for the scalar singlets, which is also complex, so it has a 2 components, real part and imaginary part. Imaginary part will be eaten by Z prime. because Z prime from where they get the mass? From the Higgs mechanism, and we agreed the Higgs mechanism, one of the degrees of the freedom of the scalars goes to the gauge positive massive. So we end from this story, we start with singlet and two doublets by two physical degrees, two physical scalars remains. One we call it phi, and one we call it chi. This is the final components remain. Due to all lambda 3, this stupid lambda 3 makes some mix between them. Otherwise, this will be like standard model, and this will be independent lambda 2 v prime mass, and that's it. But lambda 3 is not very stupid, it's good because it makes both. And then makes chi also have some interactions with the sector of the original Higgs field, the electroweak sector, our standard model sector. So this doesn't make separation and the decoupling between the two sectors, B minus L and L. So lambda 3 in the Higgs allow for mixing between chi and phi, and then B minus L sector and the electroweak sector will be interacting together. In the right-handed neutrinos, the mixing between neutrino left and neutrino right in the diagonalization also allow some interaction coupling between right and left sector, or B minus L and L. This is a matrix with lambda 3, you diagonalize. You call it now in the final states, in physical eigenstates, not in the mass eigenstates, not in the gauge eigenstates, this phi and the chi will go to H and H prime. Standard model H, we call it now standard model like H and the H prime, which is a V minus. This is the eigenvalues, two eigenvalues with plus minus. If you take lambda 3, as I told you, will give you exactly the result of the standard model square root 2 lambda 1 v, and will be called, but with a lambda 3 will have some kind of mix. And this mixing allow, as you can see, this mixing we define in angle theta for the diagonalization, and this theta is given in terms of lambda 3. If lambda 3 is 0, theta will be 0. Okay, so lambda 3 is the origin of the mixing between the two axes. Due to theta and the lambda 3, now you could have Fermi top quark, for example, top H prime. Okay, originally H prime chi has nothing to do with the top, but due to the mixing with the original standard model Higgs, now you could generate coupling H prime at top or Fermi. And this will be similar to the coupling of the standard model M Fermi over vacuum expectation value, but times theta sine theta. So theta is a small, sine theta will be small, and will allow small mixing between T and the T bar and the H prime. And this is very crucial because if you wanted to produce H prime at the LHC similar to the H, you need to generate it long fusion with this diagrams, triangle diagrams with the top, and you produce a H prime with, of course, smaller cross section due to the smaller coupling, but it's not 0. It's possible. And now even with WW H prime you could generate, and you could have H to H prime with W with some values like this. So the mixing allow for some link between the two sectors. This is what I told you about. And now this kind of mixing allows to produce H prime via this long fusion, which is a very serious channel for producing Higgs at LHC. And also you can compare now standard model Higgs in pure standard model and in the B minus L model, and also the new H prime. Because even standard model is affected, the coupling becomes MF over V times cosine. And the cosine now is not exactly 1. Cosine is changed a little bit, 0.9, but it's not 1 as before. So everything is reduced a bit. due to the reduction in the coupling. But now we gain that H prime can also be produced with normal, not normal, it's not very small cross section that can be probed at LHC. And the variation in the H standard model is not dramatically bad. Okay, this is the Higgs decay, and as I told you, the story that the coupling reduced a bit in the standard model like Higgs, and H prime has a coupling that allow production and allow decay as well. Z prime, this is the third type of new particle in this model. Also now, this has a direct interaction with all quarks and leptons because it is P minus L, and we said all particles are charged with P minus L. So, but Z prime is different than Z because Z prime directly with a coupling with L plus L minus, because L plus L minus has a charge -1, while the quark is 1/3. So Z prime dominantly goes to L plus L minus, not quark anti-quark. Z in the standard model, the quark and the quark is stronger. So this is one of the differences between Z prime and Z. So Z prime to L plus L minus is larger cross section of branching ratio than the quark and the quark. Also, Z prime can go if the right-handed neutrino, one of them is not very huge, and Z prime is 2 TeV, 3 TeV, and right-handed neutrino 500 GeV or so, it can decay to right-handed neutrino, and this will be even larger. So this is interesting because people at LHC also looking for right-handed neutrino in the BLSSM we discussed, and we showed that we can have some mixing. I repeat again the Lagrange and the masses and all this stuff. But now we can also have some discovery for right-handed neutrino, because I told you from this mixing, right-handed neutrino now can decay to W lepton or Z neutrino or H neutrino. This without the mixing of the neutrino mass mixing diagonalization really was not allowed. Also, you can produce it from Z prime. So the channel, put it somewhere, the channel of the search now of right-handed neutrino or Z prime will be proton-proton goes to Z prime, and that Z prime goes to two new right-handed neutrino right, neutrino right. This is very large, everything can gauge coupling, and it can be giving you larger cross section. And then right-handed neutrino decay to W, dominated by W neutrino, WL. And the second neutrino right goes to WL. And then W goes to L neutrino, W goes to L neutrino. So the final state will be 4 leptons and 2 neutrino missing energy. This is very clean signal for this process because the background is free. There is no standard model process that produce 4 leptons and missing energy. So people are claiming that, not people, we with some colleagues from, I think, Finland, we did this analysis and showed that this is very interesting signal to probe right-handed neutrino and Z prime, and it was published in Physical Review Letter, for example. So this was quite interesting at the time. Oh, this is here that channel. Proton-proton goes to neutrino, right-handed neutrino, and then goes to 2 leptons, maybe 2 electrons, 2 neutrinos, 4 leptons in general, plus missing energy. And as I told you, this has almost background free from any standard model similar process. So you can easily probe it and you give it to the experimentalist to check it. Okay, we take 5 minutes break, and then we do 2 Higgs doublets. Okay. I should stop sharing, or I keep it? I keep the recording. I am recording.
Maybe you can pause the recording.
I can pause the recording. Okay. Stop or pause?
Pause.
Resume. Okay.
Share the screen, we should again share. Okay. Okay, I think we can start now, or we can resume the discussion and consider the two Higgs doublet model. We just finished, we did it gradually. So standard model was one Higgs doublet, and then B minus L, one Higgs doublet and one singlet. Now we consider the possibility of having two Higgs doublets, but without extra gauge search. Just a standard model. Instead of one Higgs doublet, we will have two Higgs doublets. And as I told you, this is because in constructing the standard model, in fact, we have just one doublet, so the vacuum expectation value was in the second component, and if you wanted to give mass for the up sector, you need to consider the phi tilde, which is tau 2 times phi star, and you need to include, which is fine in the standard model, but not fine, for example, in another models. And usually you could have two Higgs doublets with two VAFs, one for the up sector and for down sector. This is one possibility, but in principle, there is no reason for limiting the Higgs boson in standard model to one doublet only, as we discussed yesterday. Okay, take it as an exercise. We try to build the standard model with two Higgs doublets. Gauge sector will be the same. We don't need to worry about any anomaly cancellation, as we said before, because there is no new fermions, just the scalars, and the scalars do not contribute in this triangle diagrams of the anomaly. Okay, so let us start with two Higgs doublets, complex, and therefore, as you can see here, you will have phi 1 with 4 components, phi 1 complex and phi 2 as well. And we will try to give vacuum expectation value, different vacuum expectation value, V1 and V2, to the field phi 1 and phi 2. Of course, the neutral components, as we did in the standard model. We will see that this type of extension with two Higgs doublet does not really affect all the prediction of the standard model, because now we will see that the vacuum V1 and V2 combine together and they give you mass for the gauge boson, WBC as usual. However, we will have rich scalar spectrum, as we will see, which may be quite interesting, and maybe also there is some hints about some discovery for different scalars, heavier scalar, or maybe even lighter scalars than the standard. Anyway, this is an example, and I think the main motivation for considering two Higgs doublet in this setup mainly comes from supersymmetry, as we will see in the lecture of after tomorrow, that supersymmetry cannot be built with one Higgs doublet. Because as I told you in standard model, you use the complex conjugate of, and you said, okay, the Lagrangian will be phi and phi tilde or phi star. In supersymmetry, as we will see, we built the theory with superpotential, which is holomorphic. So you cannot use phi and phi star. We have to use phi 1 and phi 2. Phi 2 will represent phi star in this case. We will come to this point when we discuss supersymmetry. But in principle, the motivation came from supersymmetry and from MSSM to analyze and to study two Higgs doublets. Then people take the two Higgs doublet and study it in the standard model outside the scope of supersymmetry even. Okay, so the potential, because everything in the standard model will remain, we will have only change in few things. This is the potential, the Yukawa interaction, because we will have some term coupled with phi 1 and some term coupled phi 2, or coupled with phi 1 and phi 2, or coupled with, or this is makes type 2C. So sorry, type 2 Higgs doublet will have some different scenarios. They call it type 1 2 Higgs doublet, type 2 2 Higgs doublet. It depends on how phi1 and the phi2 coupled to the fermions. But we will come to this later. Let us discuss now the potential. The two Higgs doublet potential will be much more complicated than the standard model potential, and it will be like we have phi1 squared, now we call it m11 squared, phi2 squared, m22 squared, and so on. And you have mixing term, phi1, phi2 is mass term, m12 squared. You have lambda 1, phi4, phi1, 4, lambda 2, phi2, 4. And then mixing term lambda 3, similar to the one we have in singlet scalar with doublet, now doublet. And then more mixing term lambda 4 for phi1, double phi2, phi2. All this combination are invariant under SU2 because both are doublets. So in fact, all this combination can be invariant, and therefore we have this rich or complicated potential. Many parameters, almost 14 independent real parameters, 7 complex parameters. Okay, now again, you can simplify it if you consider some discrete symmetry like Z2, and you can set lambda 6 and lambda 7 to 0, and then use some, because under Z2 you want phi1 goes to minus phi1 and phi goes to phi2, so this is where you kill the lambda 6 and lambda 7. Okay, no big deal, still we have many couplings. And in minimization, we still the original issue of having both m1 squared and m2 squared to be negative squared, because we want phi1 and the phi2 contribute to the electroweak symmetry breaking. We will not assume one of the doublets breaks the symmetry and the second one is not, because we said one of the doublet will couple with a quark sector up and one will couple with a down. So we need vacuum from each to generate the mass, because we will not use phi tilde anymore, but we will use phi1 and phi2. So we need to have vacuum expectation value from both. In fact, we said phi1 will give you V1, phi2 will give you vacuum expectation V2. And as we discussed in both the standard model and the B minus L, that to generate the non-vanishing vacuum, you need this mass square to be negative. Okay. You do this, a lot of coupling between phi1 and phi2. Usually you will have kind of mixing between phi1 and the phi2, and the phi1 coupled with some quarks and phi2 will couple with other, to generate what is known as flavor changing neutral current, and this is impose some constraint. However, this can be, not solve it, but arrange it if you follow one of these two. So, for example, model 1 only phi2 coupled to fermions. This will be like one Higgs doublet, and the second phi2 doesn't contribute to anything. It's just a couple with phi2, phi1. And this is not really interesting scenario, because this is different from what we said about supersymmetry. Supersymmetry, both phi1 and the phi2, which is model 2. Model 2, phi2 coupled to the up quark, and the phi1 coupled to the down quark and lepton. And this is exactly what will happen in the supersymmetry. So model 1 has only one doublet active and interacting with all fermions, and the second is almost decoupled, is only coupled with a phi2 and has no direct, it will couple with fermion via the mixing with phi2. But the model 2 is better than the first one, because as I told you, Susie will rely on this phi2 coupled to the up quark and phi1 coupled with the down quark and leptons. Okay. Yes.
I think you said it correctly. So that potential.
Sorry?
This potential is the one before symmetry breaking.
Yes, with the two doublets.
Okay. And all the sign of the masses is
Yeah, to generate vacuum expectation value for phi 1 and phi 2, then you need M11 square, M22 square to be negative to allow for non-vanishing vacuum. Of course, you need lambda 1, lambda 2 to avoid to have unbounded from below potential to be positive.
So you should have the negative minus sign.
No, minus sign, or you assume it is negative square.
Okay.
Similar to the potential of the standard model.
And there, then, because then you have a minus sign in front of that square bracket.
Which one?
And one.
Oh, this one?
Yes.
It's conventional. You can have it minus here, and you keep this is positive, or you put plus, and you keep this is minus. But the sign of M12 will appear from the Hessian when you study the minimization of the potential, and you make variation for all phi 1 and phi 2. The M12 will play role of the off diagonal and the lambda and all this stuff. So you will have series of constraints on the parameters to allow for existing minimum, stable minimum.
Sure. I was just asking you whether the signs are different, the diagonal curves and the non-diagonal.
I agree with you. I agree. I like in the standard model, I prefer to have minus sign here and assume M1 squared positive and minus sign here. But sometimes we keep it and we said M1 squared is negative to stress that we needed to be negative squared to have this non-zero value.
And if you take M11 and M as square as negative,
then you will have non-zero.
Yeah, and what about M1 square?
M12, this is as I said, will go to the off diagonal with other combination of this parameter. And then you will have conditions, not just simply to be positive or negative. You have to have some condition like, I give some condition here, lambda 1, lambda 2 positive, lambda 3 square larger than square root lambda 1. But there is also condition with M12, because the minimization now is more involved, and the uniqueness and the existence and stability of the minima require some positive value for the Hessian that you will derive. So all this parameter will be cooked, and I agreed with our colleagues, not our students, with colleagues, that they will work out as a homework the details of the 2 Higgs doublets, because I will just highlight things and leave it to them. And then I will inform you who did it. Okay, so as usual, we start here with the 2 Higgs doublets. So in principle, in fact, we have about 8 degrees of freedom, because 2 complex doublets, so 4 plus 4, 8. Again, we are in the standard model, so only Z boson and W plus W minus acquired mass. So only 3 degrees of freedom will be eaten from out of 8. Remember again, a standard model was 4, 3 was eaten, and 1 remained physical Higgs. Then we went to B minus L. It was 6, 4 from the doublet, 2 from the singlet. 4 was eaten because Z prime also acquired mass. So 4 was eaten, and then we remained with 1 scalar from the standard model Higgs and 1 scalar from the B minus L singlet scalar. Now we have 2 doublets, 8 degrees of freedom, and the 3 will be eaten, and now remains with 5. Out of 8 will refine. Those 5 will be, in fact, I don't know why 4. It's neutral scalars will be 3, 2 CP even, H, little h, was standard model like H, and capital H, which is a heavy CP even Higgs, rather heavy than the light H, and the capital A, which is a pseudoscalar, remains. It was 2 pseudoscalars, 1 is eaten by Z and 1 remains, because each Higgs doublet has 1 pseudoscalar. So 1 of them is eaten, 1 of them remains. So this is, we call it A. And of course, 2 charged Higgs. Before, there was 2 charged Higgs eaten by W plus W minus. But now 2 Higgs doublet produce double or 4 charged Higgs. two charged Goldstone boson eaten by W plus W minus, and the other two will be giving like physical charged Higgs. So we end with a Higgs sector which has 5 degrees of freedom. Two scalar charged scalar. One means 2, one means H plus and H minus, so two charged Higgs. And in fact, three neutral CP even, H small and H capital, and CP odd capital. So quite rich, as I told you. And in fact, in SUSY, since we have model two Higgs doublets, we have essentially the same things in the Higgs sector. So we discovered so far just the standard model like H, little h. Still, we have heavy and pseudoscalar, and we have Higgs can be also brought at edges. So this is a description. Little h and capital H is called CP even scalar, and A is CP odd. So this is will restrict some type of decay and production for each of them, as you can see here. And this is quite useful to analyze the process that you can look at it. There is possibility when one of the Higgs model 1, in fact, in model 1, when we have one of the scalar fields is not contributing in any masses and it doesn't generate acquire VEV, and also we have some unbroken discrete symmetry. So the neutral component of this, the lightest Higgs in this doublet, could be rather stable, and therefore it could be we call it in this case inert model. So certain version of the model it can be candidate for the dark matter. It's called the inert model, and this is based on, as I told you, we have some discrete symmetry to prevent any coupling and the decay of the lightest Higgs of this doublet. And a lot of people work at this scenario that we may have a scalar dark matter from the two Higgs doublets. Possible example of dark matter. So, as I told you in previous slides, that phi1 get V1, phi2 get V2. If you go and consider the kinetic term, the covariant derivative d mu phi, and the d mu phi 2, you will find that W boson acquire VEV from both. So in fact, W boson will have a gauge coupling G square times V1 square plus V2 square. The linear combination of the two VEVs will contribute to the W boson. Therefore, we call the sum of the V1 square, V2 square to carry to the original V square, because this is just again the V square, which should be 174. So this is will give the relation. And because we have V1 or V2, sometimes we define the ratio V1 over V2 or V2 over V1 as a tangent beta. So we can work with just the V and the tan beta instead of V1 and the V2. Related to the questions of Marcelo, here is M12 and the minimization appears. So you have M1 square with the same sign plus minus, and this is a minimization condition. Now you need to minimize and you need to show that there is non-zero VEV. And as I told you, this is not one single equation, it is two. And in fact, you need really to work a little bit more with the Hessian or with very careful to show that there is non-zero VEV and stable minimum, not any, not just. Here I'm giving some hint. Yes.
And both of them need to break the.
Yes. V1 and V2 will contribute in the symmetry.
Can it be that only one?
This is I just mentioned. Yes, you can do it with only one, but in this case, you take the one which get the VEV to couple with all the standard model Fermi to generate mass, and the second one will be like ad hoc addition, which doesn't do anything except it is just a couple with the original Higgs. So this is not the best scenario for 2 Higgs doublet. And also is not what happened in supersymmetry, which is based on 2 Higgs doublet, where the 2 Higgs doublet really contribute in masses and so this is what I'm talking about the minimization of the law. So you generate it and you get the minimization conditions, and you have to take this into account because the masses should be calculated around this minimum. So now, for example, all the scalar masses will be variation of the potential phi I phi j. Phi I phi j is the components of the fields, doublets, component of the two doublets, and substitute with the value. So, for example, if you take this kind of form of the doublets, like a charged phi plus and the VEV in the zero component, which is usually built on the hypercharge, it's usually in the V down components, VA plus rho plus IA equals 2. So this is what we call the charged hex, and this will be CP even, and this is CP odd, usually. Now, for the charged hex, you have the variation of the potential respect to phi I plus phi G plus, phi G minus, and you get this potential after you substitute with the minima, which you obtained from the two conditions we said. This matrix, some work will be left to you. So some work, this matrix, if you diagonalize it, you will find, this is remember, this is for the charged hex. Okay, so what you expect? You expect one of the charged hex will be Goldstone boson, so you should expect 0 eigenvalue and one non-zero eigenvalue, because I told you there is one charged hex will remain physical. Indeed, you will get one Goldstone boson. This will be eaten by W plus W minus, and now we will have one charged hex with this value. And this value will be related to this squared B1 B2 M1 squared. So the minus sign is taken out to give you here positive values for contributing to MH plus minus. If it is not taken out and kept, maybe we will have minus sign. Okay, so this is the charged hex, the first new particles different from our Higgs sector and the standard model, which is a charged Higgs. The Goldstone boson, charged Goldstone boson are there, it's eaten by W, but also we have physical charged Higgs, H plus minus. Now for the pseudoscalar, for pseudoscalars, you do the same things. And you make the variation respect to eta I, eta j. Remember, I told you I'm working in the notation where I wrote the doublets phi A as a charged phi A plus, and the down is VA plus rho A plus I eta. Eta is a pseudoscalar or the CB odd. So if you wanted to find out the matrix of the pseudoscalar hexes, you need to make variation of the potential respect to eta A, like what we do here. So for the pseudoscalar MA square IJ will be partial 2 by partial 2V by partial eta I partial J at the minimum. Very important to substitute with the minimum, otherwise you are not really doing the masses. The masses is given around the minimum after you fluctuate the field around this there's equal here will be this mass matrix, which is very similar to the charged Higgs. And now again you get 1 0 eigenvalue, which is a neutral Goldstone boson G0, which is eaten by the Z. And now we have extra, since we have two doublets, one extra remains, and this is, we call it physical Goldstone boson MA with a mass MA is given again by M1 squared 2 V squared V1 2 minus lambda 5 V squared. You should compare MA with MH plus. So if you go to MH plus, you will find it is essentially the same, apart from lambda 4 contribution in the second term. MA square will be the first term identical plus 1/2 lambda 5 V square. Here is lambda 4 plus lambda 4. So if lambda 4 for some reason 0, this will be identical equal, MA or MH plus. So the MA minus lambda 5, here is minus 1/2 lambda 5. Okay, slightly different due to the 1/2 as well, but very close, because the M12 times V square over V1, V2 may be more dominant, I guess. Sorry, guys. We return back. Okay, so I was saying that MA, the mass square of the pseudoscalar is quite close. Okay, and this is maybe important features of this class of model. In B minus L, we don't have charged. We have only pseudoscalar and independent from. Now for CB even, again, we do it partial 2V by partial rho I, rho J around the minimum, and we get this mass matrix. And this mass matrix now, in fact, it has two non-zero eigenvalues because the CB even remains, and we have in the standard model 1, but now 2 Higgs doublet give me 2 CB even scalars, non-zero, and this is what we call H for the standard model like, and capital H for the heavy new Higgs. So these eigenvalues can be non-zero, can be simplified if you combine, as I told you, tangent data V2 over V1, and you can, I think I will write to you now the expression for the masses, but from the eigenvalues, from the eigenvectors, eigenstates, you can see that the light H is given in terms of rho 1 times sine alpha plus rho 2 sine alpha. And H2, this is like what we were talking about in the right-handed neutrino and left-handed neutrino. So 2 by 2 matrix, you diagonalize with sine and cosine, and depends on alpha. So alpha is the angle, mixing angle of between H and capital H. So if alpha is a small, then light standard model like Higgs H will be mainly coming from rho 2. For example, and H coming from rho 1. If alpha is large, close to pi over 2, then the sign will be dominant and H will be coming from rho 1, or combination if it is pi over 4, so both can contribute to H and H. Okay, in principle, everything could be aligned. Now, the gauge bosons, because it is affected due to just a couple of the W boson and the Z with the 2 doublets. So here the situation, in fact, your Lagrangian, I told you already that D mu phi 1 and 2, and this will be essentially acting on both similarly because they both are doublets essentially, and both are charged under U1 hypercharge as well. So when we get vacuum expectation value, as I told you, you will get linear combination of P1 squared, P2 squared. And in fact, you can have now also MW is defined this way, MC defined in that way, and the photon will remain massless. Exactly like in the standard model, this will not be touched. So this is so far the relevant information I wanted to give you about the Higgs, 2 Higgs doublets, and I will see who's interested to complete any missing part in this discussion, and we work together. But before that, let us mention the case of the inert Higgs doublet, the one which we mentioned that may be candidate for dark matter, and also Marcelo mentioned if the one of the field has 0 VAV. So this is a case, we call it inert Higgs doublet, because one of the Higgs will be inert, means inert, is not interactive, is not interactive. So this is phi 2, I choose it phi 2, 0, 0 VAV. And the phi 1 will 0 V1. And this is a case of the inert mean. And now, since phi 1 has you coupling with Fermi, only phi 1. So it works as a standard model. You need to use phi 1 and the phi 1 tilde to generate all masses, because phi 2 is not helpful in here. But phi 2, what will do? Phi 2 will couple only with phi 1 via the potential. Because remember, we have lambda 3 phi 1 squared, phi 2 squared, lambda 4 phi 1 dagger phi 2 whole squared. So all this type of couplings, it allows kind of link between phi 2 and phi 1. But phi 2, which is the inert, has no direct interaction with the standard model family. Okay, it has interactions with W, because it's still doublets. Okay, but it is inert in the sense that really it's not interacting with the standard model. Second, if you assume exact Z2 symmetry, you will kill the mass term M12. Okay, when you kill mass term M12, remember MA was first term proportional to M12. Fortunately, we have contribution from lambda 4, lambda 5, and they are still there contributing. So MA will not be identically 0, neither also the charged Higgs. So anyway, so in this case, M12 term will be 0, and no decoupling limit extrascalar masses cannot be. Yes, because now I don't know if I have slides or not, to show you how the CBE then of this phi 2 could be stable and could be dark matter. Yeah, I have one slide about this. So the unbroken Z2 act as a conservative quantum number, and in this case, H is assumed to have Z2, and the capital Z2 equal 1, capital H, capital A, charged X have Z2 equal -1. Fermi and the gauge boson is, again, Z2 symmetry is a discrete symmetry with ±1, and you substitute, you distribute it as a way, ad hoc, essentially, as you want. Now, standard model H goes to FF bar, remain TT bar and the Fermi bar, and capital H is not. This is capital H, which will be inert, okay, because it comes from the phi 2. So I rather not call it capital H in this scenario, because it's not heavy, it's not light and heavy. It is completely inert. I call it H prime. Okay, so H will still interactive, coupled with FF bar, can be produced at LHC from glow fusions, because it coupled with TT bar and so on. H prime, or capital H in this slide, is not. For that reason, it is inert. And this is important because it will not decay, because H goes to FF bar, means it decay to FF bar. And even if it is light, maybe it doesn't decay to TT bar, but it decay to E plus A minus. It decay to any light particle, quark, anti-quark, bottom BB bar or UV bar. So the best is to forbid it completely, to have H kind of stable particle. So this Z2 symmetry and no vacuum expectation value will make H capital or H prime is kind of light and stable and inert, not interacting, so it is stable, and this is candidate of dark matter. So the lightest dark scalar, this one, will be stable and candidate for dark matter. Okay? In fact, this is one example based on this assumption, but all dark matters really you need to make some assumption. Even in supersymmetry, we need to assume some R symmetry to have the lightest particle stable. So it's not ad hoc assumption. You assume Z2 symmetry, and you assume one of the Higgs doublets do not get any vacuum expectation values, and you gain that you could have viable dark matter. Dark scalar would manifest as missing energy because you cannot produce it. It may go out with some Higgs process. It has a Higgs or H prime due to the mixing with alpha parameter, and it appears as missing energy. It is inert, so it's difficult really to. Difficult to probe it, and this is maybe explain why dark matter at xenon experiments at the direct detection, where you are looking for some interaction, direct interaction with proton or neutron, means quark antiquark, is not visible so far. However, since it coupled with W plus, because it is coming from the doublets, it may have some indirect hint via the positron flux or gamma rays flux in the sky. Also, the annihilation in dark matter, there is important criteria you have to satisfy about the relic abundance. So you cannot say, yes, it is stable, it is inert, and it will remain in the universe. Could be remains with very large ratio. We need very specific ratio of this. So some of them should be annihilated until we reach some temperature, it's called the freeze out temperature, and the remaining matter of this H prime will be the relic abundance of the dark matter. So this is very tricky, not very easy to satisfy. However, it is possible because this particle can be annihilated via W plus W minus. Okay, so inert Higgs model is very simple dark matter model, but it is heavily constrained from cosmology and astrophysical dark matter searches. Yes, because it has a couple with W plus and W minus. So the effective coupling with the proton and the neutron would be rather large. It can be even ruled out from the direct searches of underground experiment. I said there is no direct coupling with quark antiquark, and then this is good for this experiment, but unfortunately there is effective coupling via W, and W is 100 GeV, so the coupling will be 10 to minus 2, 10 to minus 3. This is not small, then you could see something, and unfortunately the constraints are rather stiff right now. Okay, this is more or less, you know, I give you a highlight and the idea about two Higgs doublet, and in the previous and the first part, it was one Higgs doublet, one singlet with some U1 prime. So maybe now you touch the basis how we can extend the standard model. And as I told you, each time you extend it with very simple idea, you get really non-simple outcomes. Here, for example, you get five Higgs, charged Higgs, pseudoscalar Higgs, heavy Higgs, in B minus and Z prime, right-handed neutrino. By the way, here you do not touch neutrino masses issue. So if you want, you should also add right-handed neutrino with two Higgs doublets. Right-handed neutrino will be added as extra particles. If you wanted to extend it with extra gauge, this will be another issue. So this is what I want to say about these two. I call it two simple extensions, and hopefully we are now ready for tomorrow. We discuss SU5 because this is not that simple extension, but it is a serious extension to the standard model with more elegant, philosophy and simple gauge group and real trial to unified forces in mind. Okay, so that's all for today. And if you have any questions, please go ahead.
Hello, can you hear me, Shaban?
Yes, I can.
Oh, okay. I have two questions. One is that, as you explained already, that we can extend the model
Sorry?
by adding.
Sorry?
We can extend the standard model
Yes.
by adding some particle contents. The other way is to extend the gauge sector. Is there any third way that we can extend the model?
I gave you you were with us yesterday. In the direction to go beyond the standard model, I think I list about 10 directions, including supersymmetry, which extends space-time symmetry, extended by extra dimensions, and will be considered in the last lecture, and supersymmetry in the fourth lecture. Extend the gauge symmetry, like what we did today with U1 prime and SU5 tomorrow. And by particle spectrum, as you said, like the Higgs extensions that we did now, and also flavor symmetry, as I told you yesterday, that the standard model based on the space-time symmetry and the gauge symmetry. However, we have several open questions about masses and the flavors and so on. So people start to think that maybe the third type of symmetry, which is called the flavor symmetry, and we may consider standard model based on this. And as usual, once you assume something in addition to the standard model, you get really quite not little information and predictions from this. So yes, in principle, yes, there is some several directions.
Okay, thank you. The other one is that, can you make a few comments on the parameter tangent beta? Because
tangent beta?
Is it like a model dependent things? Or...
Sorry, you are talking about
tangent beta.
Tan beta, yes.
Exactly.
No, tan beta is just simple parameter that instead of working with V1 and the V2, because tan beta usually we define when we have two Higgs doublets. Okay, so for example, in B minus L, we don't have two Higgs doublets. We have just Higgs doublet and Higgs singlets. So no need to define tan beta, because even the singlets is not contributing to W plus mass or Z boson mass. It is just V prime, which goes to Z prime. So there is no, but here with two Higgs doublets, you have V1 squared and the plus V2 squared combined together, as I have shown in one of slides, give mass of MW squared. So essentially V1 and the V2 are not really independent, because the sum of them is giving V squared. However, V squared is just one parameter. You need to define another parameter to have 2 degrees of freedom, V1 of V2. You replace it with V and tan beta. Tan beta is a ratio, V2 over V1. In two Higgs doublets, type 2, model 2, that we call it, or in SUSY, where we have phi2 coupled to the up sector and phi1 coupled to the down sector, we define tan beta as a V2 over V1. If you are not following model 2 and you have another scenario for 2X doublet, you can define tan beta V1 over V2 or V2 over V1. The important to watch the definition and to define something so that you replace V1 and the V2 by V and tan beta. Then what is tan beta? What is the values of tan beta? Okay, if you take it V2 over V1, like in the SUSY or in model 2, and the V2 contribute to the top mass. So in fact, you need V2 to be large enough to give you the top mass, because we said top mass is lambda times VEV in the standard model, now lambda times V2. And the top mass is 174 already. So we don't want to consider lambda to be larger than 1 for perturbativity reason. So it has to be the larger. So V2 should be much larger than V1. So in this case, tan beta could be quite large, up to 50, 60. And
this is actually what I was asking, because I saw 10 beta very high, like 20, 25, 30 in some
Yes,
models.
yes,
Yeah.
yes. This is in SUSY and the model 2 because it is V2 over V1, as I mentioned. However, in other scenarios of 2 Higgs doublet, you have 10 beta equal V1 over V2. So you find that their preferred value very, very small, even less than 1, 0.1, which corresponds to 210 in your case. So it depends on how you define 10 beta.
Yeah, thank you. Thanks so much.
Yes, please.
Is a two doublet. We assume that the first doublet phi will be coupled with the upward stuff, and the other scale phi 2 coupled with the down. So is this choice coming from specific condition or constraint that we assume for phi 1 to be able to interact with the upward stuff, and phi 2 to be able to interact with the only downward stuff? So can we exchange, assume, for example, arbitrarily phi 2 can interact?
Okay. Did you hear the questions? Sorry. As usual, the net is not very stable. But I was asking you online. Did you hear the questions?
No.
Okay, so محمد برضو ولا محمد؟ ربنا اسمعنا كلها محمد. Muhammad was asking based on what phi 1 or phi 2 will couple with up sector or down sector, can we exchange and so on. In fact, yes, it has a criteria. It depends on the charges. It is doublets, that's fine. So it allows both to couple because we need doublets, but it depends on the height. So we are back. Sorry for that, because let me pause. No record. I think this recording now, or I should. Okay, good. So sorry, the net was not stable, and we are back now. So Muhammad was asking about the condition for coupling phi 1 or phi 2 to up sector or down sector. And I was telling him this is mainly depend on the hypercharge of phi 1 and phi 2. However, you could make it like in standard model if there is no any discrete symmetry to prevent phi 1 and phi 2 apart from the hypercharge. You could have phi 1 and phi 1 tilde, phi 2 and phi 2 tilde, and then you couple phi 1 to up sector and the phi tilde 1 to down sector, phi 2 to down sector and the phi 2 tilde to up sector. So in principle, you can couple to all, phi 1 and phi 2. However, in supersymmetry and in other scenarios, we couple only phi 2 to up sectors and phi 1 to down sector. We prevent or try to prevent by some other symmetry, either discrete symmetry or some other symmetry, like in supersymmetry, the superpotential and holomorphic, so no star should be used, no complex conjugate should be used. So this is prevented the phi tilde, only phi 1 and phi 2 here and there, and that's it. And they are fixed by the charges of the U1 hypercharge. So this is but if you are not in SUSY, no discrete symmetry, then you can use phi 1, phi 2, phi 1 tilde, phi 2 tilde to overcome the hypercharge, because phi 1 tilde will give you opposite sign for the hypercharge. Okay, any here or there questions, comments? Okay, so anyone like the 2 Higgs doublets would like to explore it? Or
one of the instead of the so.
No. This is a scalar. We need the right angle between its fermions, and we need really to. No. Even as a doublet, even if you have right-handed neutrino, this two Higgs, this second Higgs doublet will not help. You need singlets to generate mass for right-handed neutrino, like in the first scenario. So, no, unfortunately, no. Okay, so think about it. If you need any questions about two Higgs doublets, I'm here. If you like U1 prime, I told you also, instead of U1B minus L, I invite some of you or all of you to think about U1 prime and see how difficult or how simple or how general it will be different from just from the B minus L. So you have to exercise right now U1 prime and two Higgs doublets. But I will not insist that one voluntarily say, I will do this, think about it, and let me know if you like it. And still, we are coming tomorrow for SU5. Any questions? Okay, so if
no, not from my side. Thank you.
If there is nothing here or there, we will see you tomorrow. Bye.
Okay. Bye, Shaba.
Bye.